All right, so a quick introduction round. So my name is Sebastian. I am the founder and CEO of a company called statworx. Some of you might have heard of us. Some of you, or probably most of you, don't. So we are a company here from Frankfurt. We are currently 80 people, and we are building AI technology for companies. So this is what we do. We are here because of an extremely exciting topic, and this is DALL-E 2. One question before we start with the content. Who actually has heard of DALL-E 2 and used it already? Okay, oh wow, okay, there's actually a lot of people. And how many people of you know how it works? Yeah, this is also a lot. Yeah? Okay, really interested to see if we can tell you something new then for tonight. So we have structured our talk into two sections. So I will do the intro and some kind of like high-level introduction into the topic. And Fabian will do the technical deep dive and explain to you how DALL-E is actually working. So that will be really interesting. And when we are then ready and very thirsty, we can head over to the cocktail bar, and I'm also looking forward to that a lot. Warm up, I always do before my talks, so a little bit of audience engagement, and I've prepared a little QR code that I would like you guys to scan now, if possible. That will lead you to a Menti site where you actually have the opportunity to select one of two choices. So what you should see now is a left and a right. Good, so what I want to do now with you is a little exercise. So I have prepared a couple of images, and we always have an original image and an artificially created image by DALL-E 2. And I want you now to decide which of those images has been artificially created. So which one has been created by DALL-E 2. First exercise. I have created one artificially images from DALL-E 2 of the Niagara Falls. So one of those images is fake and the other is real. So could you please try to guess which of those images has been artificially created? And you can Menti that up. And I will look it up on my phone because I can see the results here. And I can tell you if you're right or you're wrong. Exercise number 2 is a bit more difficult and from a different genre. It's a picture of spaghetti bolognese. So which one of those do you think is real and which do you think is fake? So the next one I brought, a painting of a church in the style of Claude Monet. Okay, so I will now give you the correct answers. Sorry for that result thing. I'm not sure how that works. So in the Niagara Falls, who of you thinks that this picture is fake? Okay, that's actually quite a lot. This one is fake? Far few people. Okay, so this is the fake one. Sorry guys. Spaghetti bolognese. This is the fake picture. I think this will be the most interesting one. So this is the real deal. So you see that even though you as human beings are claiming that you are extremely intelligent and far more intelligent than machines, at some point it becomes difficult for us what is reality and what is artificially created. This is the reason why we are on stage tonight, because we want to find out how exactly is that possible and what does it mean for us, what does it mean for creativity, what does it mean for creative industry. So there's a lot of things that are in extreme risk of being disrupted by using such kind of a technology. So I just collected some more really cool examples for this DALL-E picture here, this picture of a cat that looks like Napoleon, and so on and so on. You can also use DALL-E 2 for product design, so those are artificially created shoe imageries, but you can create also all kinds of other products. What's also really cool about DALL-E, you can create variations of the original picture. So this is the original picture, I think it's from Rembrandt, if I'm not, okay, Vermeer, sorry. And this is a variation that has been created by DALL-E. So you can also use it as a source to challenge your creativity and to use it for getting additional inspiration for your work as a creative artist. Some more examples, however, I think you understood that this is an extremely powerful technology that actually creates a whole new kind of era when it comes to work creatively and to interact and work creatively together and collaborate with a computer. So this will be a really big deal. The last thing I want to mention here is that DALL-E is actually, and also GPT-3 is also creating a new kind of AI-driven platform business. So why is that so important? So what actually happens is that also with GPT-3, I mean, you can use it as a private person to have fun with it, to play around with it. However, what actually happens is that other companies are actually building their products using the technology and then resell their product using technologies such as GPT-3 and DALL-E 2, again to their customers. So it's really a new era when it comes to monetization of AI models. And this is a big thing, and I think you're all really, really eager to find out what exactly is it, how it works, and I will hand over to Fabian.
Perfect. Thank you, Sebastian. And let's go to a deep dive session. First of all, before we start, quite easy. What is DALL-E? What is it? It's just an AI model that takes some input. So, for example, a corgi playing a flame-throwing trumpet, and it outputs, as we have seen before, outputs an image. Yeah, that's all the magic it does. Yeah? And the question is now, what happens in this blue box in between in the API that is served by OpenAI? To understand this, you have to go a little bit earlier down the road and discuss some of the papers and the model that released before DALL-E, because actually it seems like DALL-E is a really big leap forward in AI-generated content, but it's actually not that of a big leap, but rather another increment and a lot of steps that happened before in the last 2-3 years, right? So we have really to start with the history to understand fully why DALL-E is so good at generating images right now. And one of the first really important things that you have to understand is in roughly 2020, there was a paper introducing or reintroducing so-called denoising diffusion probabilistic models, DDPMs. And those are one of the integral parts that are then leveraged by DALL-E later. So we have to cover this, what are DDPMs, and I will go into more details later on in the presentation. Then there was DALL-E 1, so the first generation of DALL-E released beginning of 2021. First generation is quite different than DALL-E 2. So they're not really sharing much of the technology under the hood. DALL-E 1 uses so-called autoencoders or variational autoencoders with some sort of GPT-like autoregressive models. As we will see later on, this is not really used in DALL-E 2. Yeah? So even that you think about the naming, there seems to be quite familiar to each other, they're actually not that much. Apart from, yes, they can both generate images based on text inputs. Then, much more important, there was CLIP. So beginning of this year, OpenAI released their CLIP model. CLIP is really, really important to understand DALL-E, because what CLIP does is it embeds text and image in a so-called shared latent space. And I will go into more detail later on why this is important. But this is one of the first models that was really good at bringing together text information on the one hand side and image information on the other side, which is essential for then generating images from text. So CLIP, very important. And then there was Glide a few months later, which is also based on CLIP. And Glide is really more or less like the predecessor of DALL-E. So Glide is almost DALL-E 2 with some minor modifications, and that I also think we should actually call Glide DALL-E 1 instead of the original DALL-E. And I will also tell you a little bit about how Glide works, because again, this is really important to understand how DALL-E 2 works. So having said that, those are the increments that lead to DALL-E or DALL-E 2. And now let's deep into how it actually works. And this is the graph from the original paper that shows the whole architecture. And what is important to understand is it's not showing one neural network. Yeah, so we all know, okay, DALL-E is probably somehow related to neural networks and deep learning, but actually it's not just one neural network, but it's a couple of neural networks that are working together to create the content. And we see here all of those parts, and I will start to explain one after the other and try to tell you how they actually work together in order to create images from text. So let's start with the first component. And the first component is actually clip, as I said before, really important. So what the authors of DALL-E do is they use a pre-trained clip model. This is exactly this model that is able to learn a shared representation between text and images. And I will, on the next slide, go a little bit into deeper. So they use this model, a pre-trained one. So it's not trained together with DALL-E, but they're just using the one they already had in off the shelf. And then they will later on use it to encode the text that we are providing the model with. So what does this mean? Let's take a look at clip. So clip, as I said before, is a model that can bring together text and images using this so-called shared latent representation. Clip was trained by trying to predict image caption pairs. So the authors used a huge data set of images on the one hand side and captions on the other side, and try to make the model predict which caption corresponds to which image. So in a batch of, let's say, 10 images with 10 corresponding captions, which of the possible 10 times 10 pairs is the correct one? So if we have the image of a dog, image of a cat, and so on, and we have the caption, this is an image of a dog, this is an image of a cat. So can the model actually learn to find the right pairings in the data set? And doing so, by training this model, the actual outcome predicting the pairs is not what we're interested in. This is a nice byproduct, but what we're really interested in is this shared representation, because training the model together on images and text allows us later on to have then a nice space here, like an n-dimensional space, where we can encode images and text at the same time. So a model is able to say, for example, given an image, it represents the image as a vector in this shared space, and it does the same with text. And ideally, and because it learned to get the right pairings correct, ideally the image of the dog and the text dog, or everything that involves text with dog, are quite near to each other in this shared representation space. So we have now a shared space of images and text that we can use. This is not only useful for DALL-E, this is also quite useful, for example, for so-called zero-shot image recognition. So you can use this model and give the model, also clip, an image and 5 sentences saying, on this image there is a dog, on this image there is a cat, on this image there is a data scientist. And given this shared representation, you can look up which of the sentences is most closely in this shared space here to the image, and then say, okay, given it is most close, we are quite likely that this is a dog, for example, on the image, without having explicitly trained to predict dogs and data scientists or whatever on images. And this is really rich and really useful because it's allowed us to do arbitrary image recognition on unseen categories before, just because the model was trained on a huge data set of captions and images. So this is really cool, and we can use this. And how do we use it? We use it to embed our text that we're presenting into this clip dimension, in this latent space. So we have now, we're starting from our prompt, and we generated a numeric representation of the prompt, of the text, in this shared space with images. So we're one step closer to having an image, because we're now in a shared environment of image and text. So then we need the next step. And the next step is a so-called prior model. And what a prior model does, it takes this embedded text and tries to predict the embedding of a potential image from the text. So wait, what is this? So think about it. When we interact with DALL-E, we only have text, right? There's no image, because image is the output. So what we can do is now we can say, given our text in this numeric representation using clip, in this n-dimensional space here, what are potential image embeddings that would represent representate this kind of text. And of course, there should be somewhere around it, near to the text, but there are potentially infinite potentials, potential solutions. So and what the authors now do is they train an additional neural network to predict those embeddings of the image. So given all those potential images here, which one is the most likely one given the training data that we have? So we can do this and we can say, okay, given our acute dog sitting in the field, for example, this point here would be the most likely image representation in the shared space that represents an image that shows a cute dog sitting in the field. And this is what they do here. They use the text encoding and they predict the image encoding from it. They have two different ways how to do it. Technically quite far away. In the end, it doesn't matter. They perform both more or less on the same scale. The diffusion model is a little bit faster to use. That's why they ended up using it. But apart from that, there are multiple ways how to do it. The funny thing is, you don't need this. In theory, you could go directly from the text encodings or embeddings, the clip text encodings, to the final image. And this was also when I first read the paper, I did not understand why they needed to do this until I come to the section, which was unfortunately quite late, where they explain, okay, we don't need to do this, but we figured out that the results are much better if we do so. And the reason is, or it's at least what they claim, because this idea of textual semantics, so the semantics that are involved in the text are better represented and distilled when you use an embedding of the text itself and then try to predict the same visual semantic from the text semantic. And they figured out that doing this, the model is much better in representing details in your prompt that you're giving to the model. So if you add small details to the prompt, to the text, using these techniques, they're much more likely to actually end up in the actual image that is generated. So okay, another check mark. So now we went from text to text representation, and then from text representation to image representation. So now we need one more step, because now we just have numbers. Yes, there is an image behind the number, but we don't have the image so far. We just have numbers, and we need to come up with the final real-world image. And therefore, they have the third model, which they call the decoder model. And the third model is the decoder. It's a necessary one to produce the actual image in the end. And this is, I think, the most interesting part, because here we are coming to this diffusion models for the first time. And I just want to explain how it works. So think about an image of a dog. And if you then add on top of the image just random noise for multiple steps, so let's say 200 steps, in each step you add a little bit of random noise, the Gaussian noise, on top of the image. What will happen is that over time, over those steps, it's got more noisy, and after 200 steps, for example, it's just random noise. There's nothing of the original image left there. And now comes the trick. If we could reverse this process and say we start here with random noise and we do the same steps just in the other direction, then we end up with an image of a dog. And what we do is we use a neural network to try to predict from noise to image. And because we're doing this in really slow steps, one step by the other, it is actually possible for a neural network to learn from a little bit more noisy image, how might a little bit less noisy image look like. In practice, what the authors do and others using diffusion models is they're not predicting the actual image, they're just predicting the noise added on top of the image. And then they can use the original noisy image, subtract the predicted noise from the image, and then they get up with one version that's a little bit less noisy. And if you do this for hundreds of steps, then you end up from noise with an actual outcome of an image. And how can you do something like this? Often you see so-called U-nets. Why are they called U-nets? Because they look like a U. So you start with a noisy image, and then you have a decoder part of the U-net network, which uses convolutions to downscale the information. Then you have here a so-called bottleneck, information bottleneck, where the information has to pass through. So you're condensing the information down, and then you're upscaling the information again to the original shape. This is then the decoder, so encoder, decoder part. Why do you use this unit? Because it preserves the original scale. This is really shapes. This is really important because, as I said before, what you're going to predict is the noise added on top of the image, and therefore each pixel in the original image has also a potential noise on it, and therefore we need an architecture which can preserve this shape. And this is often done with units. They're originally coming from a segmentation task, but they're quite good to do here, or to use here. And this is also what DALL-E does then. How does this look like? Here's a really small example using Fashion MNIST. So you see you're starting with random noise, and over time, there's I think like 200-300 steps, there's something coming out of the noise. If you reverse this process. In this case here, you have a t-shirt. There could also become out a shoe or whatever. What is important here, in this example, because the model is trained on this Fashion MNIST data set, which only contains clothes, there will never come a dog out of the noise, because the model have never seen that before. And it is also completely random what kind of clothes comes out. So you cannot guide whether it's a t-shirt, a shoe, or a shirt, or whatever. Now we can go from random noise to arbitrary images, but we cannot guide it. There's no way we can say, please make a corky or whatever. So we need another step to make sure that there's actually some guidance of the model, which will then end up in a guided generated image. And here it gets a little bit more tricky, and again, we need here a clip. So what you do is you actually implement a so-called guiding process in the diffusion process, not only to produce from random noise a random image, but to go in a certain direction. And we do this, or the authors do this, by, for example, using the clip image embeddings from before and add it to the input of the noisy image. So now this unit is not longer only using as an input the noisy version of the image itself, but in addition it also have the clip embeddings that was generated by the prior. So given we have a text input, a dog, we generated the clip embeddings out of it, we predicted it using a prior model, and then we can concatenate this clip embeddings to the original noisy image. And what a model is then doing is it's saying, okay, giving a noisy version of this one here and an additional information, which is our clip embeddings, I should go from here to here. So we are guiding the model in a certain direction using this clip embeddings. They're not only using clip embeddings, they're also using this clip text embeddings as an additional input. So you're really blowing up your input side, adding a lot of additional information to it. But this has the effect that during this process here, this denoising process, the model always goes in the direction of not only the original image here, but also using image embedding and following this prompt that we provided it. And this is why DALL-E is able to create not just random images, but create random images that follow a certain prompt. It is much more, let's say, difficult if you go into the details. There's a lot of attention involved here. So it's not a standard unit. You have attentions all over the place because attention is all you need, actually. You also have to embed the time steps, so during which step we are currently in this denoising process. You need a certain normalization factors and so on and so on. So there's really a lot of technical details that you can dive in. But the overall idea is that you have this guidance using the text and you guide the denoising process. So you go from the text input to a text representation in the shared space. Then from a text representation in the shared space, you go to an image representation. Then you have this denoising model, which learns to just gradually denoise noisy images. And then you end up what we have seen in one of the other slides. And one more thing that was really important, and this I said before, the text input is really, really important of how the model generates the image later on. And also small details really matter here. And this is because we're using these clip embeddings and concatenate them to the image input. So there are a lot of people nowadays doing nothing else than thinking about how to prompt models. Yeah, this is true for DALL-E, it's also true for GPT and other kind of these language models. And there's a really cool book called the DALL-E Prompt Book, where a lot of those techniques are already described. So for example, you cannot just say, or of course you can say an image of a dog, but the image will then be just quite lame. Yeah? But if you say, for example, a close-up, black and white, studio photography, portrait of a dog, dramatic lighting, a 1973 photo of Life magazine, then you're coming up with really cool stuff. Yeah? And all the cool images that you see in the internet, they're not from really simple prompts, they're from such really handmade prompts where somebody iterated for hours maybe to trying the right setting of words to produce this kind of cool looking image. Yeah? And when we now go into the next phase and try really to play with GPT a little bit, keep this in mind, this prompt design, because the better you prompt, the better the results will be.